Hello, I welcome you all to this another interesting screencast. The problem reads, the four feet members of the mechanism are pin connected at their centers. If vertical forces P1 is equal to P2 is equal to 30 pounds, act at C and E are shown. Determine the angle theta for equilibrium. The spring is unstretched when theta is equal to 45 degrees. Neglect the weight of the members. This problem is coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Hibbeler. We're going to solve this particular problem by using the virtual work method. The virtual work method is an alternative method to the equilibrium of a particle, to the equilibrium of the rigid body, to the equilibrium of interconnected rigid bodies. It is an alternative, therefore it means we are able to solve this particular problem by using the equilibrium of rigid bodies or interconnected rigid bodies method to still solve this particular problem and determine the angle theta. But we are going to solve this problem using the virtual work method. What is the virtual work method? Virtual work method states that the total virtual work in a system is equal to 0. And this virtual work is due to summation of the product of forces and translational virtual displacement. Okay, it can also be due to the product of the summation of couple moment and rotational virtual displacement del theta. And when we sum up all these components of virtual work in a system is equal to 0. So given a force F and a translational virtual displacement del r, for virtual work to exist, the force and the virtual displacements are supposed to be collinear or parallel. And if they are in the same direction, we have positive virtual work, otherwise we have negative. If we have a couple moment m and rotational virtual displacement del theta, the two must be parallel or collinear. And if they are in the same direction, then we have positive virtual work, otherwise we have negative. So in brief, this is what virtual work is. Right. So first things first, we are going to draw the free body diagram. And after that, we are going to draw another free body diagram of the deflected or displaced configuration of this particular system after we've applied the virtual displacement. Then after that, then we'll write down or develop the virtual displacement equations, which we are later on going to use in our virtual work equation. So let's draw the free body diagram. So at the hinge A, we are going to have a reaction in that direction and another one like so. And then at the roller D, and at this point we are saying, we are assuming there's no friction, we are going to have the normal force like so. Alright, what else? And then this spring here, let's section it at this point like so. And once we do so, then we expect spring force in this manner like this, okay, and another one in that manner like so. So we have spring forces like that. Alright, so this one is Fs and this is also Fs. And then we have this one there is Ax, this one is Ay, this one is Dy. Right, we are done with the free body diagram. So what we need to do is to apply a virtual displacement. It can either be a rotational virtual displacement or translational. For me, I'm going to go with the translational. So I apply a virtual translational displacement going to the right at the point D. Okay, so I'll apply a virtual displacement in that direction like so. All right, like so. Okay, so once I do so, let's draw the deflected or the displaced configuration of this particular system. So I expect a movement, let's say from this point here, from this point, this part, let's say it is going to come up to somewhere there. All right, and then this other part there is going to come up to somewhere there, like so. Okay, all right, yeah. So let's say this is our system, this is our new system. So this point here is our, this is our E, this is our C, this is our C prime, this is our E prime. Okay, and this is our B prime. So there we go. So we are assuming the system is going to be like this. Therefore, it means at E we expect some vector displacement in this direction, like this, like this. Okay, and also going down. At C we expect this movement like so, as well as going down, and so is at B, but we are not concerned with B, but I'll just indicate it. Okay, we don't have any force there. All right, so these are the vector displacements. So let's label them. So this one is just going to be equal to del xc. This one is del yc. This one is del xe, and this one is del ye. All right, you can name this one as del xd, but we are not going to have anything there, right? We have also some rotation there at A. All right, let's concentrate with what we have. So let's choose our fixed reference, as A. So let's now define these particular points at A. So at A we are going to have, if we choose A, let's say we're going to say this direction from there, from here to there, we define the vertical. Okay, so this one is going to be both this one will be both del, this one will be ye, which is just equal to yc, right? And then for in the horizontal direction, these points in the horizontal direction, we are at the same point. Point A is equal to point E, right? Okay, and then what else? At point C, in the horizontal direction, we are moving from here like so. Okay, So this one we're going to call it as x. This is xc. Okay. So there is for xe is just going to be equal to a. So let's define the spring force. So Fs is equal to K times S, and K is equal to 200 pounds per feet, and S is equal to L final minus L original, or L naught. L naught is equal to, we've been told it's unstretched when theta is equal to 45 degrees, and we have this angle here which is also the same there. Okay, right? So this is just going to be equal to, what's the length of this member? So this is 2 by 2 cos 45 degrees. Okay, and this is just going to be equal to 4 cos 45 degrees. Then L final is just equal to 4 cos theta. Therefore, Fs is just going to be equal to 200 by 4 cos theta minus 4 cos 45 degrees. Okay, and this therefore gives us, if we are to simplify this, Fs is just going to be equal to 800 cos theta minus 200 times 4 cos 45 minus 565.69. Right, 200 by 4 by cos 45, that's 565.69. all right, let's now define the equations. All right, what do we now, let's define our virtual our coordinates, point E and C. So we have YE, which is equal to YX, YC, and this is just going to be equal to the length of these members. There are 2 of them, so this just becomes a 2. Okay, you have 2 by 2 sine theta, okay, which is just equal to 4 sine theta. The vector displacement, therefore, del YE, which is equal to del YC, is equal to 4 cos theta del theta. Okay, and then we have xc is equal to just a 4 cos theta, and the vector displacement is just going to be equal to del xc is just equal to minus 4 sine theta del theta, and this is equal to 4 sine theta del theta. Then we have the vector displacement del u equal to 0. Plugging in those, at A we don't have any vector work, at E we do have in the vertical direction. In the horizontal at E, our reference coincides with the point E. Okay, so we'll not be able to define that one in the horizontal direction, but in the vertical direction we already have it. So we are just going to say, and in the vertical direction, P1 is in the same direction with the del YE. Therefore, we have a positive vector work. So this one is just going to be equal to P1 del YE, and then at C, both the horizontal and the vertical are going to be there. The vertical also is a positive one, that's P2 del YC, and then the horizontal is negative, it's minus Fs Fs del xc equal to 0. I know you are wondering to say why Fs by del xe. Of course, the component at E is just going to be 0. That's the reason why I didn't indicate it, because of our reference. Our reference coincides with E. Okay. So let's plug in the values. P is given. P1 is just going to be equal to P2, which is equal to 30 pounds. So if we are to plug in this, we have 30 by del YE. What is del YE? Is 4 cos theta del theta, then plus P2 is 30 also. Del YC is the same also, it is 4 cos theta del theta. Then we have minus Fs is 800 cos theta minus 565.69. Okay, and this one, it is times del xc, which is just equal to 4 sine theta del theta equal to 0. So let's write this. And we simplify it so that we solve it. There we are. What do we have? We can sum up the two there. So 30 by 4 by 2, that's 240. So let's factor out del theta outside. Then we have a positive 240 cos theta, and minus that's 800 by 4, that's minus 3200 cos theta sine theta. Okay, let me move this a little bit somewhere there. All right, so this is 3200, that's minus, and then plus 565.69 by 4. This one gives us a 2262.76. sine theta, okay, equal to 0. All right, let's divide through by cos. If we did so, then we are going to have a 240 minus 3200. So here I've got to mention to say del theta is not going to be equal to 0. The only part that will be 0 is this part there. Okay, so if we divided that by cos theta, we'll have a 240 minus 3200 sine theta plus 2262.76 tan theta equal to 0. Okay, so we can solve this now. We need to solve this, and the only way out to solve this is by using the numerical technique, one of which is the trial and error. Okay, so using the trial and error method, I will say let this be expressed as the function of theta equal to 0, and let theta be in the range 0 to 90. Alright, so imagine the solution is at this point where the function of theta is equal to 0, but since this is the analytical solution, if we are to find the exact solution, but we want to use a numerical technique, therefore we want a value of negative. The function should give us theta that will give us a negative value and the other one positive, and then we'll start iterating so that we get closer to the solution by reducing the error. So this is the technique that we intend to use, and we've used this particular technique in several of my videos. Alright, so there we go. So let's go ahead and try and solve this. So here we'll plug in theta. There I'll plug in theta, a function of theta. So let's start with 0. Plug in 0 there. What does it give us? It gives us a 240. Let's plug in a 20 degrees. At 20 degrees, what do we have? Okay, that's 240 minus 3200 sine 20 plus 2262.76 tan 20. Of course, it gives us a minus 13.89. So we know somewhere in between 0 and 20 we have the solution. So let's get the average of the two. We have a positive value on the other side and a negative value on the other side. So we know between 0 and 20 we have the solution. So average of the two is 10. We plug it back. So 240 minus 3200 sine 10 plus 2262.76 tan 10. So we have 83.31. We are always getting values with the smallest negative and the smallest positive. So these are the two. Average of the two is 15. So 240 minus 3200 sine 15 plus 2262.76 tan 15. Of course, this gives us 18.08. So we're getting again the average of 20 and 15. 20 plus 15, that's a 17.5. That's the average. You plug it in. 240 minus 3200 sine 17.5 plus 2262.76 76 done 17.5. So this gives us a minus 8.81. Alright, so we get the average of gain of the smallest values. We keep on doing this iteration. So 15 plus 17.5 divided by 2, this is 16.25. So 240 minus 3200 sine 16.25 plus 2262.76 done 16.25. So we have a 4.08. We get the average of the two. 17.5 plus 16.25. Average of that's a 16.88. Let's plug it in. 240 minus 3200 sine 16.88 plus 2262.76 done 16.88. So we have a minus 2.56. We get the average of the two again. So 16.25 plus 16.88 divided by 2, we have 16.57. So 240 minus 3200 sine 16.57 plus 2262.76 tan 16.57. Alright, we have a 0.67. Get the average of these two. 16.88 plus 16.57 divided by 2, so we have a 16.73. So 240 minus 3200 sine 16.73 plus 2262.76 tan 16.73. So we have a minus 1.01. So average of these two again 16.57 plus 16.73 divided by 2, we have a 16.65. Let's plug it in. 240 minus 3200 sine 16.65 plus 2262.76 tan 16.65. Okay, 16.65. So there we go. We have a minus 0.17. Average of the two 16.57 plus 16.65 divided by 2 as 16.61. That's 240 minus 3200 sine 16.61 plus 2262.76 tan 16.61. 0.25. Average of the two 16.65 plus 16.61 that is 16.63. That's 240 minus 3200 sine 16.63 plus 2262.76 tan 16.63. So a 0.04. This is quite good. We can get another, again, smallest value there. Average of the two 16.65 plus 16.63 divided by 2. Average is 16.64. So 240 minus 3200 sine 16.64 plus 2262.76 76 than 16.64. So we have a minus 0.06. So we can end here. We know the solution is in between this, okay? All right, between 16.63 and 16.64, okay? So this is a minimum error, therefore we can go with this one. So say our theta is approximately equal to 16.63 degrees. All right, I think this is about it. We found the theta that will allow this system to be in equilibrium. All right, I hope this video was helpful, and if it was, give me your thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and I'll see you in my next screencast.